And can you see my screen?
Yes.
Okay, great. Then yeah, I'll get started. Quickly, I just want to say thank you to Alife. This is my first time as a presenter and as an attendee. And so this is a very exciting opportunity for me. So my name is Shane St. Luce. I am a PhD candidate at Binghamton University, and I've conducted some research on strategy evolution in the Farol problem under guidance with Hiroki Sayama. And so for those who are a little unaware of the problem, it started off kind of as a thought experiment by William Bryan Arthur on suppose that there's a bar that's super popular, just like El Farol in Santa Fe, and there's 100 people who want to go to the bar, but the bar only has the capacity for 60. And suppose those people do not have any ability to interact or coordinate whether or not they will go to the bar. Suppose that the only information they have is that previous bar attendance history, and they don't use their own personal history of visits to the bar in deciding when they go. And also suppose this bar is only open once a week. So this is like a weekly cycle. So that means the actors are inherently trying to avoid going to a crowded bar and optimizing to go to the bar when it won't be crowded, when they think it won't be crowded. And so each actor is given a set of predictors or strategies for them to use in their decision making. And so they may pick a predictor for a given week, and the predictor suggests that it's not going to be crowded, so they decide to go to the bar. And so inherently, since the actors make their decisions independently, they don't directly influence each other, but the decisions they make ultimately affect the overall happiness and average attendance of the bar. So I came up with the question of how does the distribution of these strategies affect overall happiness and the average attendance? And further, since they have the ability to change their strategy from week to week, how does this evolution of strategies change over time as they learn which strategies are better and which strategies are worse? And so for the sake of this experiment, I defined strategy specifically as the attendance predictor and the action that the actor takes. And so I basically came up with 3 strategies based off 3 different concepts. One is the last correct strategy, which basically assumes that the bar will either be crowded every week or the bar will never be crowded. So it's consistent week to week. And then the last incorrect strategy, which considers that the bar will fluctuate. So one week it'll be crowded, the other week it won't. And then the never strategy, which is considering that the bar will just always be crowded and essentially not really worth it. And I want to make a quick point that the last correct and the last incorrect strategies are polar opposites of each other, and they both depend on the attendance history of the bar. And so for any simulation, when they're making a decision the first week, the last correct strategy users will go to the bar randomly with about 60% probability. And because of that, the last incorrect users would go to the bar with 40% probability, exact opposite. And so to focus on the strategy distributions and the behavior of the simulations and the actors themselves, for every simulation that was created, I've made sure that the initial strategy distribution was preset, and also to I'll keep a little bit more focus on the strategy distributions. Each actor would use the same strategy every week until the strategy became really poor for them and they became frustrated. And at which that point, with about 20% probability, they'd have the opportunity to switch to an alternative strategy. So this means that each actor is given multiple strategies to choose from. And so quickly to go over the approach, basically I took each pair of strategies and ran simulations with different initial distributions and not allowing switching to see how happiness and attendance was affected. And then did the same thing with the exact same initial distributions, allowing switching, and then doing everything again using all 3 strategies at once in the distributions. So there's a set of static and a set of dynamic simulations and results. And so first I'll go into the 2 strategy results. And basically what happens here is that when 60% of the population or less are trying to use the last correct strategy, we can see on the y-axis here that the average happiness is basically 100% because the bar is never crowded. Once it hits the 60% allocation to last correct or higher, or specifically higher, the bar can get crowded when they all decide to go to the bar. So it oscillates back and forth week to week, which means the last correct strategy is actually the most unhappy scenario, and the never strategy is accurate 50% of the time. And so this chart here shows on the x-axis from left to right the extremes of the different distribution possibilities. And now here, the y-axis shows the distributions and the x-axis shows the simulated weeks. And when I mentioned recent history, the recent history is considered, in this case, 5 weeks. And once an actor uses a strategy for 5 weeks, that's when they have the opportunity to switch their strategy. So once we hit 5 weeks in this simulation, all the simulations, regardless of the initial distribution, seem to collapse towards the middle and staying towards about 30 to 70% allocation of strategy in both directions. And then it would stay there for the duration of the simulations. And so next was the never and last incorrect strategies. And it led to pretty much no happiness. And the basic reasoning here was that pretty much people would not go to the bar. The only chance for the bar to get crowded was if in the first week, the last incorrect strategy users would overcrowd the bar, but that would require 60 of them to go to the bar, when at max 100 of them would go with 40% probability. That means there's less than a 1% chance of them crowding the bar, which effectively means every week they should go to the bar, but no one does. And so because of that, the collapse towards the middle is a lot stronger here than with the previous pair, and there's a lot more activity. And that activity is simply because the actors are constantly trying to find a better strategy, but neither strategy is really helpful in this pairing. And so lastly, you have the last correct and the last incorrect pairing. And basically what happens at the 60% threshold, which appears again, is that on one side, when 60% or less are using the last correct strategy, the bar will show this consistent behavior week to week. And so it will either always be crowded or will always not be crowded. And the last correct strategy can capture that, whereas the last incorrect strategy is always one step behind. But once more than 60% of the users decide to use the last correct strategy, then it completely flips. The bar can get overcrowded, and it gets overcrowded every other week. And the last correct strategy ends up being the strategy that's one step behind, whereas the last incorrect strategy is on top of it. And so here, it looks a lot more similar to the first pairing with last correct and never. The last correct and last incorrect strategies, again, come towards the middle, except this time there's a slight, I guess, it moves slightly towards the last correct, but even still, it stays fairly in the middle throughout the simulation once actors start switching their strategy. So now for the results for the 3 strategy interactions, it's a little interesting here too, because the 60% threshold again shows up. This showed up with each pair that contained the last correct strategy. And so it kind of makes sense that it would show up here. And what it shows that a combination of things happen here. One, when the last correct strategy is used by less than or 60% or less of the population, then it didn't really matter. The never and the last incorrect strategies, or what everyone else used, because they would all just decide not to go to the bar. And that's why the happiness ends up being at its peak in this system when exactly 60% of the actors are using the last correct strategy. But once more than 60% use the last correct strategy, it starts to oscillate, like mentioning before, and the last incorrect strategy seems to have a little bit of an edge over the never strategy. So just from this alone, we might want to think that last correct, last incorrect, and the never strategies are should be ranked in that order. And then here we can see the average attendance. And again, right at a 60% threshold, that was right at the mark for 60 people at the bar on average, which is the ideal bar attendance. All right. And so with those two in consideration, this dynamic view is actually a video or an animation of how all of the simulations moves over time. And so each dot here represents one simulation, and their position in this triangle depicts the initial distribution or the distribution that they are at in this current time. And so, for example, the distributions that are at the far ends of the corners are the ones that are most using the strategy at said corner. And in this case, since there's multiple options, whenever a frustrated actor decides to switch strategies, they simply switch to the best alternative, again, based off of their recent history. And so as the animation goes on, you can see it's kind of a swarming effect. So again, we can see the behavior that I mentioned before, the never and last incorrect users want to use the last correct strategy if the last correct strategy is not being used by too many people. But eventually, an interesting thing that shows up is that the last incorrect strategy, even though it seemed second before, actually gets completely abandoned. And so I got a little more curious about this and wondered what happens when we change the switching mechanic. And suppose when, say, an actor using the never strategy has the choice between last correct and last incorrect because they're frustrated, and the last correct strategy has shown that it's correct 60% of the time, and the last incorrect strategy is correct 40% of the time, then they will make their decision on that 60-40 split. 60% chance that it'll pick last correct, 40% chance they'll pick last incorrect. And so again, as the animation goes through, it's really similar behavior, but over time, it doesn't completely get rid of that last incorrect strategy. It tries to ignore it, but every once in a while, people still choose that strategy. And then lastly, try to see what would happen if people just randomly picked a strategy. This is complete frustration. They don't care what the other strategies have. They just want to get rid of the strategy they're using. And in this case, it was a little different. It was actually really interesting because they quickly swarmed towards the middle, but there's always this group here that's right about the 60% last correct threshold. Again, it appears, but there's also a group here in the middle that gives an even distribution between the three strategies. And then there seems to be an interaction between the two, between those two areas. So I got even more curious. What happens if we bend the rules a little bit and even break a rule, perhaps? And so in this time, instead of using a never strategy, what if actors could always go to the bar? And instead of randomly going to the bar the first week, what happens if they just always decide to randomly go to the bar? And lastly, what if they're just really enthusiastic and they go to the bar whenever they personally have made the correct decision to go to the bar, to go or not to go to the bar? So for example, if the previous 5 weeks, the correct decision was to not go to the bar and they did so, they did not go to the bar, the enthusiastic strategy would say, go to the bar next week. What happens here? And so it's a little interesting because it's not as smooth as the previous graphs showed, but even still, the highest average happiness leaned more towards the enthusiastic strategy being used, or even the random strategy being used, but not the always strategy, if we were just to look at this graph alone. And then the average attendance stayed closest to the bar capacity, similar to where we would see high happiness. And so again, with the best alternative switching strategy, it would actually collapse somewhere around that area where the bar capacity was, the capacity at the bar week to week was about the same as the attendance. And so real quickly, since we're running low on time, I'll go through a couple of the other ones. Proportional showed similar behavior here. And then random also showed similar behavior. Again, kind of clustering towards that, along that line through the phase space. And so in conclusion, this was, as far as I could tell, one of the first, if not the first representation of the problem as a low dimensional dynamic system focusing on the strategy distributions. And attractors seem to appear regardless of what kind of strategies were being used, even when some of the strategies appear to break a couple of the original rules. But I think one of the bigger insights is that the higher dimensional behavior is heavily influenced. It seems to be heavily influenced by lower dimensional behavior, if not driven by it. But that doesn't necessarily mean that we can tell what higher dimensional results are based off of the lower dimensional results. And so very quickly, some things I'm considering for the future is representing inequality, because right now, since each actor is given all strategies, if we get to see them explore the whole phase space, but suppose the top half of the phase space is unavailable, what do they do? Where's the attractor then? And in fact, since now there's 6 strategies, how can we visualize more than 3? And suppose a strategy suggests to go to the bar, but the actor decides not to go to the bar. How does that disobedience affect the system as a whole? And then lastly, take this approach and try and apply it to in a more practical setting, preferably something along the lines of a socioeconomic system. So again, thank you very much for watching. My name is Shane St. Luce. Feel free to reach out to me on Slack, and this is also my email, and I'm open for questions.
So people can raise their hand or unmute themselves if they have any question, and if